As was being said before, we're part of 12993 Robokings Forum, and today we're going to talk about complicated designs, the pros and cons of choosing them, and the ways that you can make sure that if you do have a super complicated robot, um, it's optimized for good performance at a competition. Obviously, if you do decide to make a really complicated design, the chances of everything working on the first try is almost impossible. But there are a couple of things that, in our experience, you can do to really help improve your performance on the field. Uh, so today we're going to talk about reducing failure points, weight reduction, optimizing battery draw issues, improving your wiring, and blending control system with your code to have seamless driving. Grace will start.
One of our biggest issues in robot with many moving parts, like the amounts of failure points that can happen in game. Obviously, having your robot break in the middle of the game, or having, say, your climb this season break it at the beginning of end game. This was one of our biggest problems this season. As you may have seen if you watched any of our matches, the best way to optimize your robot to have as little failure points as possible is just driver practice. Some of the main things to watch out for are having game elements stuck in your robot, wires breaking down, your encoder's position being off after an autonomous period. We have a manual reset button where a secondary driver can press on the left joystick to enter a controller mode where they can manually control the intake and outtake slides and the pitch to bring them to the proper position to reset the encoders. This mode can also be used to help remove game elements from the inside of the robot. With practice in every scenario, this can help ensure a robot isn't dead at the beginning of the end game. Little free build solutions such as printed wedges that stops parts of your robot catching on each other, or polycarbonate plate in places where game elements can be easily stuck will help ensure the consistency of your robot. On top of all the small plates, where we notice issues in a robot, we use polycarbonate sheets across the bottom of a robot to protect our wires and around all our suspension and control hubs, which help ensure our important electronics are protected even in the case of harsh defense.
If your robot has a lot of moving parts, the odds are that it will be quite heavy. So for us at our nationals competition, our first build of our design simplicity was around 16 kilograms with 8 motors, 12 servos, and 16 stages of Masumi slides. Weight reduction is extremely important for your battery draw, but also for speed and maneuverability on the field. Your drivetrain motors have to do less work to move a lighter robot quickly on a field in comparison to a heavier robot. While there is a lot of weight reduction that can be done once your robot is built as add-ons, it's really important to be thinking about weight when you are doing your design. I'll give you an example of one of our subsystems this season. So, for example, this is our world outtake. So, from our nationals competition, we actually added on 2 stages of MGen 7 linear rails, but we actually managed to reduce the weight overall. So, for example, we knew that Actibotics X rails provide the best strength to weight ratio, and they also have good rotational stability. So previously, we would have used 2 or 3 X rails to brace our slides together. But this season, we found out that we only needed 5 points of contact to ensure that we had a robust outtake design. So we just used an aluminium axle instead. So you really want to focus on minimizing any unnecessary structural components. So this doesn't mean taking apart everything that makes your robot strong, just making sure that you don't have any parts that are adding unnecessary dead weight. Some of the more dramatic things that we personally did for weight reduction that can be replicated is we used a bare motor drivetrain, as you can see here on the field, which overall is a really good method of saving weight, but it's probably one of the final steps of optimization and can sometimes be a little bit unnecessary. The gearbox on a Go Bully Yellow Jacket motor weighs about 190 grams. So obviously, if you decide to take that out and disassemble it to become a bare motor, you are reducing a lot of weight. We reduced 1.3 kilograms on our robot by switching 7 motors to bare motors alone. Another thing to consider when you're reducing weight is the choice of materials. So if you're using axles for bracing, does it need to be a steel axle or can it just be aluminium? Or even in our case, we used 8mm outer distance carbon fiber tubing. In some cases, as structural bracing or on our intake tubes for where our brushes set. Also, the thickness of your plate. So if it doesn't need to be 3mm, if it can be 2mm aluminium because it doesn't have a lot of load bearing on it. Small alterations like that in CAD can really add up over your whole design.
If your robot has a low battery or uses all its battery very quickly in a match, it'll become significantly slower. There is definitely a visible improvement when driving a robot with charged battery or an uncharged battery. If you do have a complicated design, the odds are that you have many motors running together at once, and all the power needed will drain your battery quickly. On top of weight saving, there are several other things you can do to help optimize battery draw. For example, if you have motors or servos that you aren't using, you can turn them off completely while the robot is completing other tasks. You can also do this with motors. On our intake extension this year, we used a servo with an over-the-center linkage that flicked down to hold our slides into the robot when our slide encoder read the position of our slides as in. Then we turned the power off to the intake slide motor, which saved a lot of power throughout matches, as the intake slide motor didn't have to use all its power to hold our intake slides in. You can also utilize counterspringing to help alleviate load from motors and servos, such as counterspringing your outtake slides. You can see how we strung ours with rubber bands, and depending on the angle of our arm and how far our slides are extended, our arm will apply more or less force into the linear direction of our outtake slides.
The quality of your wiring is also very important for the performance of a robot. It doesn't really matter how brilliant your design is if your wiring breaks in the middle of a match and one of your servos disconnects, you are essentially dead in the water. Um, Especially if you have a complicated design, once again, there isn't a lot of space necessarily for your wires to run. And if you have long extensions on your outtake or not so much your intake this season, you'll have minimal space where you need to have multiple wires running over a long distance. Uh, Wiring is something that we've had a lot of issues with in the past season, but um, virtually zero issues with this season, and that's because we follow some of these main principles that I'm about to outline. Uh, this one's pretty basic, but it does make a difference. Wire casing is extremely important. Not only does it keep all of your wires together and allows them to not catch on moving parts of the robot, where wire casing is holding a large group of wires together, such as servo wires on your intake or outtake extension, all of your wires being grouped together will prevent super tight bends in your wires, which can lead to internal breaks over time. So if you look at the pictures on top of our intake extension, you can see that some of the joins are tighter than others. And those are joins that afterwards we've gone in and looked at our intake wiring for the new season. So you can see a direct comparison of how the wire casing can make the joins forced to be a little thicker. Number two, excess wiring in your robot leads to unnecessary bulk and also weight, which just aren't things that you want on a complicated design. Every wire on your robot can be made to a custom length. This is a little extreme, but this is what we do for our robots. So for every single one of our motor, servo, encoder, and power wiring, they're all custom lengths that are completely customized to our robot. So what we do is we take the appropriate gauge wires, either 12, 16, or 22 AWG, and we will crimp connections on both ends. So for our motor wirings, we'll use bullet crimps, or for our power wiring, we'll solder XT30 connectors onto the ends. Custom length wiring has another benefit, if you do choose to do it, of reducing your failure points and making it really easy to diagnose any wire failures. So if there are only 2 connection points on your wire, one to your servo power module, and one to your actual servo. If your servo suddenly stops working, it's really easy to check those two places rather than having to go through the entire wire that has been wired all throughout your intake or outtake extension, for example. So usually 99% of the time, if you do have an issue with the wire, because it's come unplugged on one end, which is really easy to fix. Another thing we try and do with our wiring is we try and avoid solder. So the only solder on our robot is at the end connections of our XT30 cables. Solder can crack and break over time, and if you have an internal break in a soldered connection, it's really hard to diagnose, unlike a crimped connection where you can see very obviously if something is unplugged. They're also significantly harder to replace. If you do choose to use solder on your robot, though, try and keep the connection still, and also make sure that you seal it properly with double-walled heat shrink so that you have as little chance of it breaking as possible. If you have a complicated design where your wires need to move in extremely complicated positions, as you can see in our bottom right picture with our bidirectional horizontal rails on our outtake, make sure that you try and avoid harsh turns and twisting motions of the wire. As you mentioned previously, it can cause internal breakage from repeated stress at a singular point in your wiring. You can see here that even though our wiring there's a lot of it and it's all throughout our robot, we've really tried to avoid any particularly harsh turns. And you can see for our outtake slide wiring, we have a method where we just twist our wire so that it coils in around a 7.5 centimeter loop at the bottom of our robot, and then that extends as our slides come out. While our intake slides, we mount them on what is essentially half of a scissor linkage because we needed to reduce the weight from a full scissor linkage, which allows us to have a rigid point of extension that we can attach our intake wires to. Finally, make sure that you're using ferrite chokes on all your important wires, so especially your odometry wires, to help avoid noise and ESD as much as possible. Another thing we do to help avoid any issues with that is we isolate our hubs and also our servo power modules as much as possible. So we have a 3mm PLA plate that we print that sits between our metal inner side plate and our control and extension hubs. And then we also have layers of tape between our robot and our servo power modules. So just little steps like that can help you avoid future issues.
So, should talk a little bit about planing code and improving your driver control. I think the first part is remembering that software is a direct extension from your hardware. So you can have your hardware being limited by unoptimized software and software being limited by hardware fails. So if you have a complicated robot with a lot of moving parts, it's physically impossible for a human driver to perfectly align, adjust, and control all aspects of a mechanism quickly. So teams should use partial automations with sensors, such as detecting the game elements or your intake to automatically move your robot transfer sequence and go to outtake or whatever. So just go through your normal sequences, but automatize this process as much as you can. This helps minimize the possibility of human error and increase the consistency of the field. Overall, during teleop and autonomous, your hardware can also be limited by inefficient and unoptimized code. This will directly impact your PID performance and therefore impact your accuracy and your consistency throughout the field. Complicated robots with more moving parts will tend to have much higher loop times, which will cause inaccuracies and inconsistencies in your performance. It is possible to help manage these high loop times through strategies such as wiring all your sensors to one control hub and co-creating it, caching your hardware calls to keep the robot from queuing any unnecessary calls when the target position of a servo or motor hasn't changed, mode threading for your IMU, and having a separate read class that will prevent the robot from doing any double reads or double writes. Read relevant sensors feedback, so any I2C or any protocol that takes a little bit longer, you only have to read the sensor when you actually are in a state on your finite state machine that you need that feedback. So there's no point reading our distance sensor on our claw while we're on the intake state because that's not being used. So that helped us manage our loop times from around 200 milliseconds right after our bot was finished building forwards to around 20 milliseconds by the end of the season. Thanks you all for listening. This is our presentation, and please feel to ask any questions.
All right, does anybody in person have any questions? Yes.
Is there you recommended pushing all of the code to, or putting all of the connections for the low latency on one hub. Is the bulk read time dramatically different? I mean, does it, and when the bulk read is for the encoders, right? Not for just general power.
Yeah, so as you said, yeah, you can bulk read sensors, but bulk reading encoders and everything, the most important part is that the connection through both hubs are kind of slow, especially if you're using the data cable and not a USB with photon. So when you bulk read, so for our example, we have all of the encoders we use most states, so like our outtake and our pitch that need to be constantly read through all of the states, being on our control hub, but on our expansion, we have the intake slides and stuff that we don't have to keep reading the encoder all the time. So you can manage if you put your bulk reads to manual, and you can do, there's a little bit of a code snippet that you can figure out which hub is the parent one, so the control hub or the child one, which is the expansion. You can put them to manual, and then you can just read one of them. That is about 8 milliseconds. I found it out during season 2, like 12 for us. It was saved from doing that. So I would recommend, if you have time, it's like one of those final optimizations, and it might be a little bit challenging to make it because you also have to hardware everything to only one hub that might not be the closest hub to your actual mechanism. But I would say it's pretty good way of improving your robot.
Thank you.
Okay, do we have any other in-person questions? If not, then everybody make sure to thank Robokings 12993. And of course, if you have any other questions, just make sure to put them in the chat and they will answer. Thank you very much.
I do see a couple of questions in the chat. Are we meant to answer them, or are we meant to leave?
Feel free to answer any questions in the chat.
There's a question that said, what do you use instead of soldering to make your wire the correct length? So it really depends on the wire. For, say, your servo wires, you can buy crimp connectors online from Amazon, which look exactly like the connectors that you have on your servos. So the servo wire generally is 22 AWG. So what we do is we just cut and then we crimp them with crimping tools. I don't have a picture of that right now. For our motor wires or the slightly thicker wires, we use bullet crimps. And then for our XT30 wires, the power wiring, we just solder the XT30 connectors at the end of the cable. There's a tutorial online on how to do that properly.
Okay, and I think that in the interest of time, we can have the responses to chat questions, just type them in the chat so we can have the next team present, if that's okay.
Okay, thank you so much.
Thank you.
Thank you so much for presenting.
Thank you.
Let's have another round of applause for Robokings.